Okay, so we can start today's class.
Thank you.
That is all about Earth's atmosphere. So in our yesterday class, we tried to discuss on what is space, what is universe, what is galaxy, and what are the composition of the universe, what are the composition of the galaxy itself. And then finally we arrived to one of the galaxy in which we are belonging, that is called Milky Way galaxy, and the dimension of what is the dimension of Milky Way galaxy, how we can measure the distance in between galaxies or distance in between planets. So once we come to Milky Way galaxy, we try to see what are the major planets in the Milky Way galaxies. So the one which surrounds Sun, that is one of the smallest part of Milky Way galaxy. So we try to understand what the 8 planets which are revolving around the Sun, and there is the 9th one which is considered as a dwarf galaxy currently. And also other phenomena like the comets, the meteoroids, the asteroids. So these small rocks which are just revolving around the Sun. And we categorize planets into 2 distinct groups based on the density of their property, like the interstellar galaxies and the giant gas galaxies, which are very away from the Sun. So we have seen those important points yesterday. And then we try to discuss on the Earth itself. So what is Earth, what is Mercury, what are the composition in the Mercury, in the Venus. So this is what we have discussed yesterday. So if you have any question in yesterday's class, please let me give you a chance, and then we'll continue to today's class. Any question?
It's not a question, but do you have the recording for the yesterday's class?
Actually, some recording is interrupted yesterday, so I will record it myself and I will send it to you. So don't worry, I will prepare it because
you can also send us the PowerPoint.
Don't worry, everything I will share with you.
Okay.
Yeah. So shall we continue for today?
Yes.
Okay. So let me, before starting today's class, do you have any query on the way how I am presenting the lecture? Any query? Just be frank, this no problem. We can discuss everything in a frank way. It means no more hiding anything. Just tell me if anything that I can improve.
From my side, I don't have any query.
Others?
Me also, I like it. Okay. It's fine.
So then we will continue on the same manner, maybe in advanced way. Okay. Today's lecture based on the Earth's atmosphere, because we come down to Earth, we finish all the galaxies, the space, and other things. So the remaining thing is we start from the Earth's atmosphere. That is the point where every activities or human activities and our vehicle designs also based on those atmospheric environments. So let's start with this. So at the end of this lesson, you are expected to know what is the Earth's standard atmosphere and its composition, identify the vertical structure of atmosphere and its property, variation with altitude, and derive an equations relating the variation of atmospheric pressure or parameters like pressure, temperature, density, speed of sound, even the what we call this gravity also vary with the altitude difference. Okay, so these things, and finally do practical examples on or exercises on these points. So that is the main core point of today's lecture. So here we'll define some terms like absolute altitude, geometric altitude, potential altitude. These are some kind of, when we call altitudes, we can see some various altitudes. Sometimes we measure altitude from the Earth's center. Sometimes we measure altitude from the point where sea level. Okay, Earth's center and the sea level are different. So based on that, we consider altitudes with different meaning. And sometimes we measure the altitude based on the position of the vehicle or the moving vehicle in the atmosphere. So such kind of definitions are there. Constitutions of the standard atmosphere means the vertical structure, which we are going to see. And definition of pressure, temperature, and density with respect to altitude. Okay, so these things will be also the part of this discussion. And the some physics phenomena like hydrostatic equations and the gas equations also become to picture under this discussion. So let's come to the Earth's atmosphere. So whenever we are designing a vehicle, that vehicle must is based on the consideration of these atmospheric properties. So design vehicles to remain in orbit or to travel to the atmosphere requires knowledge of environment. The pressure, density, and temperature of environment influence the magnitude of aerodynamic forces. So when we are moving with very fast motion, that aerodynamic forces are imposed into the structure or the vehicle, and which induces thermal stress on the vehicle. Okay, so these things must be under consideration. So on the vehicle, well, the composition of environment affects the chemical and electric interactions with the vehicle surface material. So the structural designer must consider this whole phenomena, because this high pressure, high aerodynamic forces have tendency to collapse the structure, and then our mission will collapse also. So the Earth's atmosphere may consider be comprised of number of concentric spherical shells, which are, we call them as some zones, or and one from another there is a transition zones. So that we call them are some troposphere, stratosphere, mesosphere, ionosphere, and so on. So such zones are should be discussed in the level of today's discussion. So that can be actually presented with some picture. I will show you the picture. Look, these are the pictures which shows us the Earth's atmospheric condition clearly. In this picture, what we can see at the bottom here, we can see stratosphere, and a thin line which separates stratosphere from another top layer is called no, I mean the bottom one is troposphere. So troposphere is the very thin layer which separates troposphere from stratosphere, and the next layer is stratosphere. So each of these spheres are separated in some distance level. We categorize them by providing some distance from the Earth's altitude. Okay, so and then after stratosphere, there is a thin layer also there, that is stratopause, and then mesosphere, then mesopause, then thermosphere will be the next to the up to the von Karman line. It is considered as thermosphere. So that can be clearly described in this picture. You can see here. In this picture, what you can identify is the variation of density with altitude. For example, if you see this line, how density vary with altitude, pressure with altitude. If you see green line here, it shows the pressure variation with altitude, speed of sound with respect to altitude. Look, the speed of sound varies with altitude. Again, and then temperature variation with altitude. Okay, there is temperature variation with altitude. So most of our discussion is based on the temperature variation with altitude, so that just give emphasize, then the remaining parameters will be discussed based on this. Okay, so mainly we consider on temperature versus altitude, then what are the variation of other parameters on that point. Okay, so at the same time we can see what are these things. Look, there are some deep space, we call some deep space also there, which is below the atmospheric level, means 0 sea level. Below that, we can see some deep space. On that, some ships are operating into some deep space. That is considered about 11 kilometers down to the sea level. And you see here, there is it says some Burj Khalifa. What is Burj Khalifa? Anybody knows?
Yeah, it's a building in Dubai.
Huh?
A building in Dubai.
Actually, that is one of the building in exactly, I don't know the location. Saudi Dubai, I think. That is
Yeah.
one of building, one biggest building in the world. So the level of Burj Khalifa also, Mount Everest levels are under troposphere. Every these things are under troposphere. Okay, and then there are some aircrafts which are flying above troposphere, like currently that this Concorde aircraft is already out of the business because of some issues. So Concorde aircrafts are supersonic transport aircrafts which are flying above troposphere. SR-71 Blackbirds, these are also the type of aircrafts which flying above. So ozone layer also the part of stratosphere. Okay, ozone, the ozone layer, we consider ozone in the stratosphere. And some weather balloons are also fly in the stratosphere zone. Okay, so this is some of the vehicles which fly on the stratosphere zone. And then meteoroids are running in the zone of mesosphere. Meteoroids, ionosphere zones are also continue from here. Then mesosphere is there. Some auroras are also there in the thermosphere. So these are the classification of atmosphere or the vertical structure of atmosphere. So once we understand this, I already discussed those things, but just to clarify, troposphere is in the region from to 14.5 kilometers. We have troposphere zone, and within that, temperature constantly drops. As you see from this picture, in the troposphere, temperature constantly drops. Initially, it was in degree Kelvin. Most of our calculation based on degree Kelvin. So here it is given in centimeter. No, degree centigrade. Anyways, yeah, it is in Kelvin. Yeah. So this is 288.1.15. The temperature. No, I mean at this point, temperature 288.16 degree Kelvin. So that is initially at 0 sea level. Then after it drops to this point. So I am very sorry, maybe light is off now, and we may face some internet problems soon. Hello, yes, I'm much, you know?
Ah, Isama.
Mabrat
Isama.
internet natan chilalan.
Okay.
Hello?
Isama.
ከተቋረጠም ከሆነ ደቂቃ በኋላ ተመልሰን ማብራቱ ሊመጣ ስለምችል ስለምንገባ እንትን አዌር ነው ብዬ ነው። አጥተን እስከ 11 ኪሎ ሜትር ድረስ ይሄ ፖይንት 11 ኪሎ ሜትር አልቲቲዩድ ላይ ነው። 11 ኪሎ ሜትር አልቲቲዩድ ላይ ስንት ነው የሚመጣው? ያን ካልኩሌት አድርገን እናመጣለን በኋላ how to calculate the temperature drop, then we'll discuss it later. So here it is, I think 212 አካባቢ ነው። So we'll see that. ስለዚህ temperature drop ያደርጋል and then constant temperature እዚህ ጋር ይኖራል። So እዚህ region ላይ we have lapse rate, that is change in altitude over change in temperature. The lapse rate will be calculated at this zone, and what will be, this is isothermal region, that means temperature, constant temperature region is this, and this is called the gradient region. So we'll calculate in the gradient region as well as isothermal region for various altitudes. Okay, so in the troposphere is a small layer which separates troposphere from stratosphere. Okay, so these are the first layer. The second layer is stratosphere, so on which it is up to 50 kilometers from the sea level. Means starting from troposphere, then the stratosphere will continue to 50 kilometers. So the temperature in this region increased due to absorption of ultraviolet radiation from the sun, and the ozone layer which absorbs the scattered solar ultraviolet radiation. So እዚህ አካባቢ በአብዛኛው ultraviolet ray ከፍተኛ የሆነ radiation አለ። There is also stratosphere, that is a thin layer. Okay, ኦንላይን ላይ ናቸው አይደለ?
አለ።
ኦኬ ማብራቱ ስለመጣ እንደኛ ሀገር እንደሄደ አይቀርም።
Okay.
Okay, so with the temperature gradient drop to 0 and then become negative. So on that region we can again see the stratosphere region, እዚህ ጋር temperature initially 0 ይቆይና እዚህ አካባቢ change in temperature የለም። Then after positive increase እያደረገ ይሄዳል temperature ማለት ነው። So that is what this zone. Then the next one is Mesosphere, which continue to 90 kilometer ድረስ ያለው ዲስታንስን እንደገና Mesosphere የምንለው ነው። ያ ማለት የቮን ካርማን ላይን የሚባለው እዚህ በሜሶስፌር አካባቢ ነው የሚገኘው ማለት ነው። So in this layer the temperature gradient is negative because again let me show you back. እዚህ ጋር ደግሞ ስታዩ temperature gradient ኔጌቲቭ ነው። ለምን? እዚህ ጋር lapse rate-ን ብታዩት ኔጌቲቭ altitude ነው የሚያሳየው። ልክ እዚህ ጋር ኔጌቲቭ ስሎፕ እንዳየነው ስሎፑ እዚህም ኔጌቲቭ ነው። እዚህ ስሎፕ ፖዚቲቭ ነው የቅድሙ ላይ። So this is what we call the Mesosphere zone. So on which the drop in the level of temperature is to 100 degrees centigrade drop ያደርጋል። So there is also a small region that is Mesosphere zone, which separates Mesosphere from other ionosphere, and so this region includes stratosphere. Fully, then we call this region what we have covered, like stratosphere, mesosphere, mesosphere የምንላቸው በሙሉ ተደምሮ middle atmosphere የምንለው ነው። Okay, so that is called middle atmosphere. Then thermosphere will continue. That is እስከ 600 ኪሎ ሜትር ድረስ ያለው region under this category. So that is called thermosphere. So in thermosphere region, temperature increase with altitude because of solar excitation, and therefore the temperature level reach depends upon the degree of solar activities. So temperature range from 600 Kelvin to 2000 Kelvin in this region. And the mean temperature we consider in the thermosphere is 1000 Kelvin. So this layer is we call upper atmosphere, because the previous three layers are middle atmosphere and the fourth one is upper atmosphere. And then exosphere and ionosphere are also there, which are the positions where space shuttles are moving. Actually, the space shuttle here, you can see this is space shuttle here. So, Atlantis የሚባለው የናሳ ስፔስ ሻትል ነው ማለት እንትንን ደርሶ አትሞስፌር ከሙን ሚሽን በኋላ ወደ ኤርዝ መጥቶ ላንድ ያደረገው የአትላንቲስ የምንለው ስፔስ ሻትል ነው። ሶ በዚህ በኩል አድርጎ ዞሮ ነው ወደ ሎየር ኤርዝ ኦርቢት የገባው። ስለዚህ ስፔስ ሻትሎች እስከ ኤክሶስፌር ድረስ እንደሚበሩ ነው። And so the composition of the first 100 kilometers of atmosphere is essentially contain most of the atmosphere እስከምናውቀው nitrogen, oxygen እና other gas like argon, helium, carbon dioxide, neon, krypton. So እነዚህን ጋዞቹን ነው በአብዛኛው ሎየር አትሞስፌር የሚይዘው። We know that the abundant composition is nitrogen, that's 78%. Oxygen is the second abundant composition of the atmosphere. So the maximum number of composition are oxygen and the nitrogen. For most thermochemical purpose, the atmosphere is containing binary mixture of nitrogen and oxygen. So these are the main gas of thermochemical purpose. Now let's do some small derivations, and then based on that derivation we'll take some examples, or I'll give you some examples or assignments based on this. So assume that there is an element, very small element having dimension of 1 by 1 with some DH, means differential thickness DH, and which is subjected to hydrostatic pressure or hydrostatic forces. Hydrostatic forces እንል በሁሉም አቅጣጫ ኮምፕሬስ የሚያደርግ ማለት ነው። So that consists pressure from this side and pressure from the top and the bottom. There are body forces, that is the rho GH. The body force is rho GH. So once we consider this, let's take first the perfect gas equation, that pressure is equal to density times RT. This R is the gas constant, temperature is the T is temperature. Once we have this equation, then from this element, using the summation of force along vertical direction is equals to 0, means static equilibrium condition, we can find dP is equals to minus rho g dH. So this is another equation. Okay, this is the second equation. So rearranging second equation, we can get this one. That is dP over dH, which is equal to minus of rho g. Now, again rearranging equation number 1, we have this equation, third equation. So we can substitute equation number 3 into, in terms of density, we substitute on 2. Look, we have density here, dP over dH is equals to minus rho g. So we replace density here with P over RT. Then what we can get? That we can get is dP over P is equals to minus of G over RT dH. Okay, so this is the main equation which we need. to calculate other parameters. And then in troposphere zone, there is a temperature drop. Temperature drop from point to point. For example, from 1 kilometer altitude, what is temperature? 2 kilometer altitude, what is temperature? 10 kilometer altitude, what is temperature? That temperature drop is expressed. Actually, this one is plus. It is not minus. It is T naught plus AH. H is the altitude. That is measured in kilometer or meter. A is the lapse rate. That is the slope of temperature gradient line. So what we are talking is, it is in the gradient position, gradient line. Gradient line ስንል ምን ማለታችን ነው? ወደ ኋላ እንመለስና ይሄ gradient line ነው። ይሄ የቴምፕሬቸር gradient line ነው። So ይሄ ስሎፕ ምንድነው የሚባለው? ላፕስ ሬት ነው የሚባለው። ይሄ ላፕስ ሬት which is change in altitude over change in temperature. Okay, change in altitude over change in temperature is called the lapse rate. So which is calculated to value of minus 0.0065 Kelvin per meter. This is Kelvin per meter, or someone can write it minus 6.5 Kelvin per kilometer. Kilometer ወደ ሜትር ስንቀይረው ይሄን ነገር ሲካፈል ለሺ ያደርግና ይሄን ቁጥር ይሰጣል አይደለም? And the temperature T naught at sea level, it is considered as 288.16 Kelvin. So we can use this relation. So let's see, when we substitute equation number 5 into this equation, what we can get? This equation number 6. ከዚህ በኋላ ያለው ምንድነው? It is just a simple mathematical expression. It is just differential form ነው የተሰጠን። ስለዚህ differential form የተሰጠውን በኢንተግሬት በማድረግ የሚያስፈልጉ ፓራሜትሮችን ማግኘት ነው። So we have to integrate it for P naught to P2. P naught is the sea level. This እዚህ ጋር በአብዛኛው ኖት የሚለው ነገር ስታዩ sea level መሆኑን ነው። Okay, this 40 ደቂቃ ጨርሰናል ያለ ነው። ሄሎ
ይሰማል
40 ደቂቃ ጨርሳችኋል ያለ ነው። ለስ የሆነ ሰዓት ላይ ያቆማል፣ እንደገና ሪስታርት እናደርጋለን። ኤኒዌይስ ሶ ይሄን ኢንተግሬት እናደርጋለን። እዚህ ጋር in terms of DH ነው የተሰጠው። ስለዚህ in terms of DH የተሰጠውን ደግሞ ወደ in terms of DT በመቀየር, because DH over A is equals to DT, or lapse rate is equal to DH over DT. That means change in height over change in temperature. ካለን lapse rate equation ተነስተን እናገኘው ነው ማለት ነው። ስለዚህ እዚህ ቦታ ላይ ምንድነው የተካነው ማለት ነው? DT over A. Okay, ስለዚህ ያን በመቀየር እንደገና ኢንተግሬት እናደርጋለን። So 1 over PdP which is equals to minus of A naught AR. እነዚህ ነገሮች ኮንስታንት አድርገን ነው አስዩም ያደረግነው። በነገራችን ላይ gravity is not constant, but we assumed gravity as a constant gravity. እዚህ በ troposphere ኤሪያ ላይ ኮንስታንት አድርገን ወስደን ነው። ያ የግራቪቲ ቫሪዬሽን እንዴት ነው የሚለውን we'll see it later. So G naught means G it is equal to G naught ብለናል. So which is T naught to T2. T2 is any arbitrary temperature. T2 is any arbitrary temperature on some altitude ማለት ነው. From this what we can get finally, እንግዲህ ማትማቲክሱን በደንብ መያዝ አለባችሁ። ብዙ ማትማቲክሶች ከዚህ በኋላም የሚመጡ አሉ። ስለዚህ ምንድነው ይሄ የሚሰጠን ln of T which is equal to G naught AR ln of T. T from T naught to T2. ያ ማለት ምንድነው? ln of P2 minus ln of P naught, which is equals to minus G naught over AR, the whole ln of T2 minus ln T naught. ይሄ ማለት ደግሞ በሎጋሪዝም ወይም በናቹራል ሎጋሪዝሚክ ኤክስፕሬሽን ln of T2 over T naught። ይሄ ማለት ደግሞ ln of P2 over P naught ማለት ነው። ያን e raised to በምናደርግበት ጊዜ እዚህ P2 over P naught ይወጣል። ይሄ ፓራሜትር minus of G naught over AR ምን ይሆናል? ለዚህኛው the power ሆኖ ይሄዳል ማለት ነው። ማትማቲክስ በደንብ ማትስን ማጥናት አለባቸው። ሪቫይዝ ማድረግ መቻል አለባቸው። then after we can get P naught over P2 over means pressure at any altitude P2 over pressure at sea level P naught, which is equals to T2 over T naught the power of minus G naught over AR. So this is the expression which you are finding. በአብዛኛው እነዚህ ነገሮች ኮንስታንት ናቸው። G naught 9.81 ነው የምንወስደው ብዙ ጊዜ። that means it is 9.807 ነው on the center of earth ላይ በምንወስድበት ጊዜ። lapse rate A ደግሞ minus 0.065 ነው and the gas constant R is 287 ነው። ስለዚህ ይሄ በምናቃልልበት ጊዜ ማይነስ ማይነስን ያጠፋና ፕላስ ያደርገዋል። ሶ pressure 2 over pressure naught, which is equal to temperature 2 over temperature naught, the power of 5.2586. So this is a simplified form of በማንኛውም ሰዓት ቶሎ ለመስራት እንዲመቸን ነው። በተለይ በሎየር አትሞስፌሪክ ሪጅን። Similarly, we'll calculate for density, the density variation. So density variation ለመስራት ይሄ ኢኩዌሽን ሳቲስፋይ ያደርጋል። እንዴት ነው ይሄ ኢኩዌሽን የመጣው የሚለውን ለማየት let's consider a state equation in two different positions. At the lower, let's consider P1, rho 1 RT1, P2 is equal to rho 2 RT2. Then using this, dividing equation 10 to 9, then we can get rho 2 over rho 1, which is equal to P2 over P1. P2 over P1 ላይ አግኝተናል። ምን ማለት ነው? P2 over P1 means T2 over T naught, the power of minus A naught over AR. No? So we substitute this instead of this here in the substitution. Then T2 over T1 over T2 ማለት reciprocates እናደርገው -1 ይሆናል አይደለ? The power of -1. So we have density 2 over density 1, which is equals to T2 over T naught, the power of minus G naught AR minus 1. So which is equivalent with this quantity. Why? Because here 5.2586 minus 1, that means 4.2586. Simplify የምናደርገው ምንድነው? ካልኩሌሽን ጊዜ ላይ ጊዜ እንዳይወስድብን ሲምፕሊፋይ አድርገን ብናስቀምጥ የተሻለ ነው። ለዛ ነው። በነገራችን ላይ ይሄ የሚሰራው only in the to 11 kilometer altitude only ነው። This formula works for the gradient line till 11 kilometer only. After 11 kilometer, the equation is different. Okay, so we must identify these regions. So the next one for the yeah, this is just recapping of the previous thing. Recap ያደረግን ነው። ምንድነው እዚህ ጋር ሪካፕ የምናደርገው? At sea level line, we have pressure in Newton per meter square. That means standard representation of pressure 1.01325 times 10 to the power of 5, which is Pascal. And density 1.225 kilogram per meter cube. And temperature at sea level 288.16 Kelvin. So these are some parameters which we use for our calculation. So now let's go to isothermal line. That isothermal layer means the layer after the gradient line. ኢንክላይንድ ላይን ካለበት ቀጥሎ ያለው ስትሬት ላይ ነው ማለት ነው። So let's see what isothermal layer is. Look, እዚህ ጋር የምታዩት ከ11 ኪሎ ሜትር ጀምሮ እስከ 20 ድረስ በምንሄድበት ጊዜ በስትራቶስፌር አካባቢ ያለው ምክንያቱም ይሄ ትሮፖስፌር 14.5 ኪሎ ሜትር ላይ ያቆማል። ግን ይሄ ግራዲያንት ላይ ነው እስከ 11 ኪሎ ሜትር ብቻ ነው የሚያገለግለው። ከ11 ኪሎ ሜትር ጀምሮ እስከ 20 ኪሎ ሜትር ድረስ ያለው ሪጅን ስትሬት ላይን ነው። ይሄ ስትሬት ላይን means constant temperature or isothermal condition ነው። For that, what is equation that helps us to calculate the temperature, pressure and other parameters? So for isothermal region, the same this dp is equals to minus rho g naught dh. From the state equation we have p is equal to rho rt. So the same equation are involved. And when we integrate these equations, what we can get here are p over p1. P1 means the lower means that እዚህ ጊዜ ማሰብ ያለባችሁ p1 የምንለው 11 ኪሎ ሜትር ላይ ያለው ፕሬሸር ነው። ፕሊዝ ሪሜምበር አድርጉት። እኛ አሁን እያወራን ያለ ነው the distance from 11 kilometer to 20 kilometer ነው እያወራን ያለ ነው። that means it is not from the zero level. ስለዚህ what is the pressure in the 11 kilometer መጀመሪያ ካልኩሌት እናደርጋለን። what is temperature in 11 kilometer መጀመሪያ ካልኩሌት እናደርጋለን። ቴምፕሬቸሩ ይታወቃል because constant temperature ስለሆነ 11 kilometer ላይ ስንት ነው ቴምፕሬቸር? 212 አካባቢ ዲግሪ ኬልቪን ነው። then ይሄ ፒ ደግሞ ቀጥሎ ያለው ፒ ነው። pressure at some 14 kilometer, 15 kilometer, 17 kilometer. So this is the relation for pressure. This is also relation for density. So here rho 1 is the density at 11 kilometer. Imagine this rho 1 is density at 11 kilometer. It is not density at sea level. Okay. So you have to calculate density at 11 kilometer first. Then you can calculate density at any arbitrary distance from